field extensions. So if you have a field containing a smaller field, another field containing the same field, and you multiply them over the smaller field. This, in fact, the whole machinery of taking tensor product of field extensions is essentially identical to Galois theory, because there's a way of building Galois theory geometrically in such a way that multiplication of vector fields becomes multiplication, has a geometric meaning. The idea is that there is parallel between coverings of topological spaces and field extensions. So the field is embedded this way, and of course the coverings are mapped that way, but this is, as usual, you have contravariant functors which connect these two cases. This tensor product of fields corresponds to taken products of coverings, fiber products of coverings, and then, for instance, what is Galois covering? It's a covering which has automorphisms over M primes, over the base, automorphisms which exchange fibers of preimage of a point. It acts transitively on free images of a point, and here, and for fields, the Galois extension is an extension which has sufficiently many automorphisms. This group of automorphisms should be have the same cardinality as dimension of k big over k small. And to define Galois covering, you can take Galois covering as a covering, Galois extension as an extension such that this tensor product k times k is k direct sum with itself n times. And Galois covering is a covering such that this fiber product over M prime is M, again multiplied by taking co-product. So you take n copies, disconnected union of n copies over M prime. And you can build these parallels along in such way, long way, in such a way that you will get the whole Galois theory as a Galois theory of coverings, as a kind of Galois theory for field extensions, and field extensions as kind of Galois theory for coverings on topological spaces. But today I will just speak about tensor product of field extensions. Okay, there was something we have already discussed at some length. I'll just repeat the definitions. So, field extension is a bigger field containing a smaller field, and we denote it by k big colon k small. This is the notation for field extensions. Okay, element x in K is algebraic. If x is contained in a finite dimension subfield. So let's say, and this extension is finite if the dimension of k big over k small is finite. So element is algebraic if x belongs to a finite extension of the field k small. Otherwise, it's if it's not algebraic, this is the same as to say it's transcendental. Now, there is something we have already discussed, that some product, sum and product of algebraic numbers is algebraic. This is because if you have, well, the argument is more or less tensor product again. So if you have x1 and x2 inside k big, algebraic, then you have a finite, so you have finite dimensional, so this is algebraic over k small. Then k, you take k and you add x1. This is finite dimensional over k small. Then you can add to this field element x2. K of x1, you add x2. And since x2 is already finite, what it generates is finite dimensional over k small, this means that this is also finite dimensional, so it's finite dimensional over k. So this is everything you can generate from x1, and x2 is also algebraic. This is standard, and in fact we have discussed that a lot in the beginning. And now algebraically closed K is algebraically closed. If all algebraic extensions are trivial, or finite extensions, doesn't matter. Of K are trivial, and example is C. This is something we have discussed. So now I fix a bit of conventions. So today, well, I will give a distinction between K algebras and K rings, because so far we never had any algebras which don't have unity, but today we have algebras without rings without unity, so I will call them K algebras. It's the same as rings over K. So it's rings which are also K linear spaces, but maybe possibly without unity. So we don't fix unity here. Of course, unity is unique because if you have it's commutative algebra, so if you have two different unities, like U1 and U2, x multiplied by U1 is always x. So this means that U1 multiplied by U2 is always U2. But then it should be equal to U1 if U2 is also a unity. So unity is unique, but there are examples of rings which don't have unity. For example, T, well, it's not ring in our terminology, but it's definitely algebra. In the terminology, this kind of, so the ideal like ideal T, K of T in polynomials, it's closed under multiplication, associative, but it's not, it doesn't have unity because everything is divisible by T. So this has no unity. But today I will be mostly interested in finite dimensional algebras. Finite dimensional over a field, like finite extensions, for instance. Okay, the idea is that all finite extensions of a field are related to polynomials. So consider finite or just finite dimensional algebra. So we have finite dimensional algebra to the first observation, which is pretty trivial but important. So suppose you have A is finite dimensional algebra. Over K and with unity. K is a field. Then suppose that A has no zero divisors. Then A is a field. Okay. So this is almost trivial to see it. You want to invert an element x inside your so consider element x inside this algebra A and consider operator of multiplication by x. Mu x of y is xy. This belongs to endomorphisms over K of this finite dimensional space A. And this endomorphism, it has no kernel because our algebra has no zero divisors. So kernel of mu x is equal to 0. And this implies, because it's finite dimensional, that mu x is surjective. And this implies that there exists y such that mu x of y is unity. And this implies that xy is 1. So x is indeed invertible, and the whole thing is a field. If we don't assume existence of unity, this is false. Let me give you an example, very easy. So we take an algebra K, say, of epsilon, and epsilon square is 0, and this one-dimensional of, by epsilon square. Embed epsilon, K of epsilon. So this is an algebra where all multiplication is 0. Multiplication is 0. It has no unity. Well, this is a trivial example, but you don't need to have it 0. Say take epsilon K of epsilon and take a quotient by epsilon power n. Then the basis of this algebra is epsilon, epsilon square, and so on, epsilon n, and all multiplication shifts your this filtration. So multiplication by epsilon, epsilon goes to epsilon square, and so on. So it has no division, no, well, yeah. Of course, this has zero divisors. But in fact, you will see at some point that if you don't need to assume existence of unity, in fact. It will exist a posteriori if it has no zero divisors. You will see. Okay. Now you have X inside A, which is finite dimensional over K. Then you can take a subspace generated by subspace generated by 1, x, x squared, and so on, xn, and so on. This subspace is finite dimensional because A is finite dimensional, so it belongs to A. And this implies that there are linear relations between these vectors in A. This means that there exists a polynomial P such that P of X is non-zero and P belongs to K of T. Okay, there could be many such polynomials. Take the polynomial of minimal degree. So definition. A polynomial P of T such that P of V, for instance, is equal to 0, P of T belonging to K of T, and V belongs to A, finite dimensional algebra over K. So suppose you have such a polynomial, is called minimal polynomial for V if P of T has minimal degree. Has minimal, of course it should be non-zero. Has minimal possible degree. Of course, there is a standard notion from linear algebra, which is a special case of this formalism, because if you have an operator inside the ring of endomorphisms, it generated finite dimensional commutative ring. And then this minimal polynomial is a special case of this general formalism. Not very special, in fact, it's equivalent. Okay, so now claim. So you have finite dimensional algebra, V inside R are finite dimensional with unity. And P of T, the minimal polynomial. Of V. Consider it subalgebra. So the subalgebra K of V inside R, subalgebra generated by V. Then this subalgebra is a quotient of polynomial algebra by the ideal generated by polynomial algebra by the ideal generated by P. Okay, so let's prove it. It's a standard part of, like, the first step of Galois theory, in fact. So I suppose that many people know this, but maybe in a different form. Okay, so proof. Yeah, it was here, it was RV, so let's call it RV on the blackboard. And here it should be also RV. So by definition, RV is a quotient of the polynomial ring by the ideal of all polynomials such that P of V is equal to 0. This is a definition. I mean, this is a ring generated by V, and it's so the polynomial ring is mapped to R of V surjectively, and the kernel is precisely these polynomials. On the other hand, and there is actually today I put a handout to which you can use to remind yourself that K of T, the polynomial ring, is a principal ideal ring. Principal ideal rings means that all ideals in polynomial rings are generated by a single polynomial. And of course, this single polynomial is minimal polynomial because it's minimal degree. So this ideal, I is generated by the minimal polynomial. And we're done. Questions? Was I a bit clear? Okay, thanks. Okay, and another consequence of this polynomial ring being principal ideal ring is that it is factorial in the sense that it has prime decomposition, which is moreover unique. Again, this is in handouts. I'm not going to explain why it is so. In fact, it's maybe even in school program. So here it's a theorem. K of T is factorial. So the proof is in handouts for today. Okay, and now definition. Polynomial P is irreducible if it's not a product. P of T is not a product of polynomials of smaller degree. Okay, and turns out that this is equivalent to the corresponding ideal being prime. So in fact, there are three things which are equivalent. Proposition. You have a polynomial p inside p of t in k of t in the polynomial ring. Then the following are equivalent. First, p of t is irreducible. Second, the corresponding ideal generated by p, its principal ideal, is prime. And the third, the quotient k of t by p is a field. Okay, so proof is really short. So last two are equivalent because of something we have already proven. So first, it's prime if and only if this quotient has no zero divisors. This is definition of prime ideal. But then, if you have no zero divisors and your ring is fine dimensional, the quotient is a field. I mean, it is a field. So this is a field if and only if it has no zero divisors. So every prime ideal is in fact maximal by this result. So these two are equivalent because finite dimensional algebra over K has no zero divisors if and only if it is a field. Okay, now irreducibility, if it is not reducible, then the quotient is clearly not prime because if it has two components, so if you have, if the quotient, this ideal is prime, p of t is prime, then p of t can be a product of q of t times q1 of t times q2 of t of smaller degree. Because since they are smaller degree, they can belong to this ideal. So their product should be non-zero modulo this ideal since it's prime. So this can't happen. So this implies, from prime, it implies that the polynomial is irreducible. Okay, and the converse is follows because it's a factorial ring. So if you have two polynomials, so like for non-factorial ring, this doesn't follow. You might have elements which are non-decomposable, but then the corresponding ideals are not prime. However, this is still true where, so I implies, the first assumption implies the second because p, because polynomials are factorial. Indeed, suppose you have p1 times p2 divisible by p. By factoriality, and p is irreducible. So by factoriality, you can decompose everything into a product of indivisible elements, and the p will be present in this prime decomposition for p1 and p2. So P1 or P2 contain P as their prime, well, as a multiplier, prime multiplier, or prime factor. And then this means that they belong to P. Okay. This is one more bit of Galois theory about primitive extensions. We'll use it later because it's an important notion which is used in stating and proving Noether lemma. So definition. K, you have an extension. It's primitive if K is generated by a single element, by X in K. Generally speaking, nobody, in fact, in characteristic 0, every finite extension is primitive, and this is non-trivial theorem which we'll prove at some point. Today I'm not going to prove it, but I'm going to prove a smaller, weaker statement, claim, but it's a statement which is almost trivial. You have any extension, finite extension, so it's generated, admits a chain of subfields. So you have K big, which contains K1, contains K2, contains and so on, contains K small. And each of these extensions is primitive of these successive subfields. Is primitive. This is because you can add one element, you can add one more element, and you can do it again and again until you arrive at K big. It follows from induction in dimension. Unless your field Ki is already K, you can add one more element, you obtain K, or you can obtain intermediate field which is strictly bigger than K1, and then you repeat. This, by the way, this chain is called composite of extensions. So each of these extensions are factors of the composite, and the whole thing is a composite of extensions. It's just terminology. So every extension is a composite of primitive extensions. Okay, this was a bit introduction to Galois theory. Now I will proceed to something which is slightly less well known. So I will use this strange terminology, Artinian algebra. It's properly, I should say, Artinian finely generated algebra, because Artinian algebra is an algebra which satisfies Artin axioms, namely, it's an opposite of Noetherian. Noetherianity is when you have increasing chain of ideals, always terminates, And Artinianity means that decreasing chain of ideals always terminates. But when an algebra is finitely generated, an Artinian is just finite dimensional. So I will use slightly abused notation and define A is Artinian if A is finitely dimensional over K. So Artinian algebra. As a vector space over K. And I want to assume existence of unity. And A is semi-simple. Semi-simple Artinian. If A has non-nilpotence. Yeah, so there's an easy example of construction of you can construct if you have two Artinian algebras, you can produce one more, namely taking a direct sum or several. So if you have R1 dot 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 Rn are Artinian algebras, are Artinian over K. Take R1 plus R2 plus R3 and so on plus Rn. What it is? It's just it's a collection of vectors in R1, R2, R3, and so on, which you can add and multiply term-wise. So, for instance, if you have R1 dot Rn, this is an element of this algebra, you multiply it by R1 prime dot Rn prime. This gives you R1, R1 prime, R2, R2 prime, and so on, and up to Rn, Rn prime. This is the result of multiplication of two vectors in the direct sum. Okay. You can also denote it, of course, by Ri direct sum. And I'm going to prove a useful result. Well, two results. First, I'm going to prove that a tensor product in characteristic 0, a tensor product of two fields is not always is a field, but it is always an semi-simple Artinian algebra. And another is a structure theorem for semi-simple Artinian algebras. I'm going to prove it as well. So if A is semi-simple Artinian, then A is direct sum of Ki, where Ki is an extension, it's a finite extension of K small. So this is the plan. Yeah, and this decomposition is uniquely determined by the algebra. So there's, you can, of course, you can rearrange the components, but otherwise it's unique. There's no other way of, no other automorphisms except rearranging the components and automorphism of each field. So the decomposition is unique. So the key notion which you use is idempotent. The idea is that, look, you have this direct sum of rings. Suppose they have unity. Then you can take each unity gives you a certain element in the direct sum, which is no longer a unity because it multiplies by 0 on other elements. So how we can distinguish the unity from of a direct component if you don't know about the direct sum decomposition? The answer is you define unipotence. So E inside R is unipotent. It's an algebra or ring. Unipotent. Yeah? Idempotent. Thanks. Yeah, of course. Idempotent. Thank you very much. If E square is equal E. Okay. Yeah, the important thing that there are some idempotent elements which are multiplied and give 0. So we say that E1, E2 are orthogonal idempotent. If E1, E2 equals 0. And the example, which is pretty important, is 1 minus E. So 1 minus E squared is 1 minus 2E plus E squared, right? But E squared is E, so this is equal 1 minus E. So if E is idempotent, then 1 minus E is also idempotent. So if E is idempotent, then 1 minus E is also. Very good. Okay, and it has a very nice corollary, which already gives you a certain direct sum decomposition. So this remark or the claim. Suppose that E is idempotent in R. And R has unity. Then R is ER, direct sum, with 1 minus E times R. Okay, so first, this is direct sum decomposition. Well, they don't intersect. This is the first observation. They don't intersect because if x belongs to ER, intersect with 1 minus E R, then EX is X, and then 1 minus E X is X, but then 1 minus E times E is equal E minus E is equal 0. So this implies that X is equal 0. On the other hand, you can decompose any element into a sum of, if you have some X in R. So this is, this intersection is 0. ER intersect with 1 minus E, R is 0. So to prove this direct sum decomposition, it remains only to decompose any element onto this two components. It's not hard. So if you have X inside R, let's consider EX and 1 minus E times X. sum of these two elements is actually equal to x. But the ex belongs to this, 1 minus ex belongs to that. So this is really a direct sum decomposition. And these are subrings because E is idempotent. So if you multiply element from this subring by itself, it will be also divisible by E, and the same is true for this because this is also an idempotent. So every time you have an idempotent, you have a direct sum decomposition for your Artinian ring. So now I'm going to show that every Artinian algebra without nilpotence actually contains an idempotent. Of course, this is trivial when this Artinian algebra already has unity. So a posteriori, this would imply that a given Artinian algebra without nilpotence has unity, and this is convenient. But right now, we just want one idempotent, so let's do it. This is theorem. Let A be Artinian algebra. Without nilpotence. Then A contains a non-zero idempotent. Good. Okay. So the first observation is that well, if it has so step one. Well, step one is that this ring it's Artinian and Noetherian because it's finite dimensional. So in particular, it has an ideal which A contains an ideal I, which is like minimal, has no smaller ideals. Of course, it can be A. This just means that A has no ideals, that all elements are invertible. Okay, so I can be considered as a subalgebra. In fact, then if we can prove this theorem for the ideal I, we are done. Because then it has idempotent, and then this idempotent is idempotent in A. So we already can assume that I has no proper ideals. Okay, so step two. If Z belongs to A, then this non-zero. Then this square is non-zero because A has no nilpotence. A has no nilpotence. Okay, and since we have already assumed that A has no proper ideals, this implies that I, or we cannot do it for Z. So suppose it's not in A but in I, and I has no proper, I, Z I, Z square is non-zero, so the I is non-zero ideal, but it's contained in I, so it should be equal to I. Because I is chosen already smallest possible ideal. There are no proper ideals which are smaller. Okay, and now we can use the same argument we already used earlier. Step 3, and so I is fine dimensional. I is fine dimensional over K. And multiplication by Z from I to itself is surjective, as follows from this observation. Then it is injective, then it is invertible. Okay. Now the last, well, not the last, but the most non-trivial step, because, okay, invertible, but we didn't assume that I has a unity, so we can't apply the argument which we did earlier when I claimed that if you have a ring without zero divisors, then everything is invertible. This is, I mean, there is no unity, so you can't apply this directly. You need to do something smarter, so let's do it. So you have elements Z, Z square, Z third, and so on, Zn, and so on, inside the ideal I. And they have linear relations, similarly like something we had already discussed that, because it's fine dimensional. So there is a polynomial relation. There exists a polynomial relation, P of Z is equal to 0. Now, of course, this polynomial relation starts with Z power A. So it's a sum Z AI, Z power I equals 0. But then we can, since we're already inside I, and Z is invertible inside I, multiplication by Z is invertible, we can always, if you have such a relation, you can always take, so suppose that the multiplication starts with I equal L to N, then this implies that sum from I equals 0 to N minus L, I Z power I minus, we start with L to N, and then then we subtract L is equal to 0. Because you can always, multiplication by Z invertible, so you can, if you have such a relation here, you have such a relation obtained from this by division by Z. This is equivalent, because Z is invertible. Okay. This is a relation, of course, this is a relation in I. And this is a relation inside endomorphisms of I. Because unity doesn't belong to I. And here it starts with 0. So here it started with L, here it starts with 0, with a constant, which we assume non-zero. Okay, but we expressed identity. We obtain that identity in I is equal to a z plus b z squared plus c z cubed and so on. With a, b, c coefficients in k, small. So the last step, step 5. So denote this by u. U acts on some multiplication by u, mu u is equal to identity. So this multiplication by u on I. And this implies that u squared is equal to u. And we're done. So we found a unipotent inside this smaller possible ideal. Idempotent and smaller possible ideal. This is the idempotent. It's a strange argument, but it's not that big. So in the end, we obtain an idempotent in any finite dimensional ring without nilpotence. I told you that if we have nilpotence, it's immediately false. There was this example of epsilon times polynomials, which has no idempotence, obviously. Okay. If you remember, we had this theorem telling that if you have a ring finite dimensional without zero divisor, it's a field. Now we can even make it even stronger because of this theorem. So corollary. Suppose that A is finite dimensional ring over K small without zero divisors. So it's Artinian ring. Divisors. Then A is a field. Proof. Okay, A has nilpotent. Sorry, idempotent. By this result, I mean, if it has no zero divisors, it has no nilpotence, you can apply that. But then idempotent E. Well, if it has some, so then E E times A is a field. It has unity. And then A is a finite extension of that. Also has a unity. I mean, if it is not a unity, you can, well, I leave it as an exercise. Yeah, the idea is that multiplication by E is an isomorphism. Let me tell you. So EA is a field, but multiplication by E from A to A, it has no kernel, so it is surjective. This means that all elements X in A specify E X belongs to image of E, and this implies that EX is equal to X. Because for any square of E equal to E. So if you multiply element in image of E by E, it will give itself. And then E is unity in A. So the idempotent in such a ring without zero divisors is unique and it is equal to unity. Am I clear? Should I repeat? I can repeat it. So if you have finite dimensional ring over K without zero divisors, then A is a field. First, it has no nilpotent, so it has an idempotent by this complicated theorem. So you write EA. EA is obviously a field because E is a unity in EA. E is an idempotent, so E squared is, but then EA is the whole thing because multiplication by E is injective. There is no zero divisors, so multiplication by anything is injective. So it has to be surjective because A is finite dimensional and any injective map from A to A is surjective as well. So this is a field which is equal to A. And E is the unity in that field. Okay. Another corollary, which is also very useful. It's something that I promised to do earlier. Suppose you have a Artinian semisimple ring. So A is semisimple Artinian. Then, well, here we'll probably assume the existence of unity because, well, you can prove that it has a unity. Well, maybe not. A is semisimple Artinian, then A is a direct sum of fields. Okay, so proof. Well, if it has no non-trivial ideals, in particular, this implies that it has no zero divisors, because a kernel of a zero divisor, I mean, if you have x, y is equal to 0, then you can consider the kernel of multiplication by y. It is an ideal. So, if there are no ideals, it is a field. So suppose then this means that you have, unless it is a field, you have a non-trivial ideal. So I inside, let I inside A be a non-trivial ideal. Okay. Then I contains a unipotent. This is something we already proved. I contains E being idempotent. Okay, so here I really assume, in fact, that semi-simple with unity. This existence of unity, I don't think it's necessary. So you can try to sit down and, as an exercise, prove this result without unity. Well, I'm not going to use it. So in practice, all rings will have unity. Okay, an idempotent. It was denoted here by A. You have 1 minus A times our ring A, direct sum with A times ring A is equal to A. This is a direct sum decomposition. And each of these subrings has smaller dimension. So by induction, we can assume that this is a direct sum of fields. And this is a direct sum of fields as well. So we have decomposed any Artinian ring to a direct sum of rings, unless they have an ideal. They don't have an ideal, so this means that all elements are invertible, and then they're just fields. Okay, I promised to give you structure theorem, and I almost did it, but there's a part which I didn't mention yet. It's uniqueness of decomposition. So its uniqueness, of course, up to exchange and transposition of your up to permutation of the components. So theorem. Well, it's lemma here. Let's call it lemma. Suppose you have A is equal to direct sum Ki. Direct sum decomposition, and all Ki are fields. Then this, well, let's write two decompositions. So you have direct sum plus of Ki and direct sum of Ki prime. Then Ki and Ki prime are exchanged by are obtained by so Ki is equal to K. The set is equal to that set up to permutation. Well, now it's not permutation because it's just a set. So the set of fields here is the set of fields there. Well, yeah, because there could be some repeating fields, so let's say just this is the sequence Ki prime is obtained from Ki by permutation. Okay, so let's prove it. Proof is simple. So every decomposition gives you a sequence of idempotents. So you have let's call A1 dot AN idempotents. So it's unities in K1 dot Kn, and B1 dot Bm, it could be different number a priori, are the unities in K1 prime dot Kn prime. They're unities in this field, so they're idempotents in A. Then you have some, well, you can consider the products of pairwise sum of AI bj, this is equal to 1. And all these elements are idempotents. And then AI bj multiplied by AI prime bj prime is equal to 0 unless I is equal to I prime and j is equal to j prime. So we have a collection of idempotents, and you can use this collection to have a bigger decomposition. Well, for each of these idempotents which is non-zero, you obtain that I bj times A is a subring. But this is a subring which is obtained from Ki by multiplication. So it's equal to Ki times bj. Because AI times A is Ki. Okay, so it is a quotient. It's a quotient of the ring Ki, of the field Ki. There are no quotient fields. That's not zero. So B j times Ki is equal to Ki. You can see it from this direct sum decomposition. So you have this collection A1, or let's call it Z1 dot Zn. This is collection of elements. So your Bj is Z1, Z2, and so on Zn. This belongs to a direct sum of Ki. And you multiply it by B by A1, which is just unity in the component number I. So the rest of the multipliers of the components in the direct sum are multiplied by 0. So they disappear. And the only possible non-zero product is this product which belongs to Ki. So this is why you have by Bj times Ki is equal to Ki. And the same argument proves that it is equal to Ai times Kj prime, so it's equal to Kj prime. So in that direct sum decomposition, so this is direct sum decomposition of all A. Each Ki occurs once, and each Kj prime occurs only once, and they occur in the same, in one of the summands together. So this means that the products Ai, Bj are mostly 0, and ones which are non-zero, they actually give a bijection between these fields and that fields. This is how a bijection looks like. So this is the subfield quotient in the first, the factor in the first decomposition, this factor in the second, and they are the same. They're equal. Should I repeat? Mm-hmm. Okay, so suppose you have this direct sum decomposition. It gives you a sequence of unipotents. Your unipotents are unities in K1 dot Kn, and there is another sequence of idempotents. Sorry, it's idempotents in K1, unities in K1 dot Kn, and there's another direct sum decomposition gives you unities in K1 prime dot Km prime. This is M. And these idempotents a priori can be different. If they are the same idempotents, you are done. So now what can we do with the with this idempotence, we notice that sum of AI is 1, sum of Bj is 1, so this product is 1. The product is 1, so this sum is 1. But all these elements are idempotents. In fact, they're orthogonal idempotents. Because if you multiply AI times Aj for different I and AI times AI prime, this is always 0. So these are orthogonal idempotents. And this decomposition gives you a direct sum decomposition. A is equal to direct sum AI Bj A. So now this is direct sum, this is idempotence, this is direct sum decomposition, which always occurs if you have unity represented as a sum of idempotents, which are orthogonal. And this gives you the same decomposition. We already had it for just 2 orthogonal idempotents, but you can always have it for all. Okay. Then you have a projection from this direct sum from each component of this direct sum to to the components of the direct sum and to components of this direct sum. But this projection is defined on fields. If you have a map on fields, it's either identity or 0. So this means that the map from this to direct sum of Ki is identity on some components and 0 on other components, but since this is an isomorphism, it is 0 only on the components which are 0. There is another projection to direct sum of K J prime, which has the same property. So each component here is mapped to one component there and to one component there, and it's mapped to 0 by 0 to the rest of the components. So if you pick a component here, you take its preimage there, and take its image there. This gives you a bijective correspondence between components in that direct sum decomposition and components in this direct sum decomposition. Is it better? More or less, yeah. Well, it's useful. It may be different from Schur slightly, but it's useful because then when you do Galois theory, it helps. Okay. I'm not going to do Galois theory today, but I'm going to tell a bit about, well, it's commutative algebra or algebraic geometry. The important part of algebraic geometry is a part which tells about finite maps. The reason is that there's a result about lifting. So the ideals, every chain of ideals in, if you have a finite map, which is a map, well, like n-to-1 map, you have an ideal there, you can pull it back, and it's essentially one-to-one correspondence. At least what is, well, not one-to-one, but if you have a chain of ideals upstairs, it gives you a chain ideal downstairs. If you have chain ideal upstairs, it can be lifted to an actual chain of ideals upstairs. There's a correspondence between ideals if you have finite n-to-1 correspondence between two algebraic varieties. Now this was the algebraic geometric meaning of that. So I'm not going to give main details. I'm just going to give you the formal definition from commutative algebra. So if you have a ring A mapping to B, B is finite over A if it is finitely generated as a model. And you have the corresponding map from spectra, so from the corresponding algebraic varieties, spec B is mapped to spec A. It's called finite map of affine varieties. And lots of results in algebraic geometry are proven by you take a finite map to something simple, like, for instance, just a coordinate Cn, coordinate space. You can prove this is that anything admits a finite map to coordinate space, and then you, for instance, you can do dimensions and stuff using this approach. Okay. So today I will explain why this every point has finitely many preimages under the finite map. So theorem. Suppose you have fx to y, f finite map of affine varieties. So it's algebraic sets. And you have y inside the y is a point. So it's a maximal ideal. Then f minus 1 of y is finite. This is sort of the first step on the way to build equivalence between ideals upstairs and downstairs under finite maps. Okay, so proof. Step 1. So you have the ring OX is finitely generated as OY model. This is the definition of a finite map, obviously. Okay, then R, which is OX multiplied by over OY by OY quotient by MX by MY. This is the maximal ideal of point Y. Is finitely generated over OY quotient by MY. This is because this ring, because R is equal to OX times MY quotient it's OX quotient by MY OX. This is something we already had, right? This is a property of tensor products. You can, this is because a model times R by I is equal to M quotient by IM. And this is it. But this is finitely generated as OX model because it's a quotient of finitely generated OX model, which is OX. Okay. So this is finitely generated, but this is a field. So we obtain that R is finite Artin algebra. So we obtain that a dimension of X by MY or X, and that we take this dimension over OY I quotient by my, which is, in our case, this is just C. It's finite. This OX quotient by my my OX is Artinian. Okay. So now step 2. Suppose that this ring was denoted by R, and N is nil radical. N is nil radical in R. Then the preimage f minus 1 of y is spectrum of R quotient by N. This is something we had last time in the previous lecture, that if you are interested in the algebraic variety f minus 1 of y, you just take a tensor product of this type, and you take the quotient by nil radical, and you obtain a ring which would be a ring of regular functions on that set, on that algebraic variety, on this algebraic set or on this affine variety. Okay. And now, step 3. We have this R by N is semi-simple Artinian. This means that it has finitely many maximal ideals. Well, each maximal ideal corresponds to a summand, which is a field, because it is a quotient by something and this quotient is a field. And of course, everything is generated by idempotence, so this includes the ideals. So the ideals are just direct sum components. The ideals in this R by N is direct sum of Ki. And if you have an element which is non-zero in some so every ideal is just direct sum of several components of that decomposition, but maybe a smaller number. And then the maximal ideal are just quotient fields. And you can obtain a quotient field from this direct sum just by killing all components except one. So there are finitely many. This follows, for example, from this argument which I gave to you about the uniqueness of the decomposition. Okay. I promised to you to give one more result, namely explain why the tensor product of fields is a field. And this is a nice stuff. It's not hard and it's pleasant. So let me do it. Okay, so definition. Suppose you have a finite field or just a ring. So it's an algebra, K algebra. And you have a bilinear form, G over K. So G from R times R to K is invariant bilinear form. If g of a x, y, z is equal to g of x, y, z. So the typical example example, if you have one belongs to, if you have unity, so if R contains unity, then g of x, y1 is equal to g of x, y by this invariance. So you have there's one-to-one bijective correspondence between invariant bilinear forms and one. So every hom over k small from R to k is in bijective correspondence with bilinear invariant forms. So if you have theta from R to k, then define g theta of x, y by taking theta of x, y. This is one direction, and in opposite direction, how to recover theta from g, you just take theta of A is g of A1. And by this formula, there's one-to-one correspondence. So this not a complicated business. There are lots of them, but there are some other bilinear forms which have not, which have different nature. Well, there are some examples. I'm going to skip them because we're already late. Yeah, so now we're interested in non-degeneracy. So definition, G is non-degenerate if for each non-zero element in R, there exists y in R such that g of xy is non-zero. So this is more or less automatic for that kind of products because you just take you take anything on which theta is non-zero, and you if theta of A is non-zero, then g theta of x a x minus 1 is non-zero. So if you have a field, this is always non-degenerate. Okay. But the main example is not this. The main example is trace. So definition. Suppose you have k big over k small is a finite extension. So you have x and y inside k big, trace of xy is a trace of the corresponding operator, is trace of mu of the multiplication by xy. So it's a trace of a map A goes to xya. This is clearly bilinear. And invariant, because it depends only on the product xy. Okay, and it is non-degenerate because trace of 1 is the dimension of k over k small. So it's non-zero unless you have your infinite characteristic. So non-zero if char k small is 0. So you really have this bilinear product. Now, we won't have much time, but at least I should tell you a couple of words about what happens when you are in characteristic non-zero. In that case, this is again a part of Galois theory. You need to define separable extensions, and it's there are several ways of defining it, but in fact the most clear way is using trace. So definition, a field extension k big over k small, find is separable it's a term of Galois theory if the corresponding trace form is non-degenerate, well, non-zero. If it's non-zero, it's automatically non-degenerate by this argument. Okay, char k is equal to 0, then everything is separable by this observation. So I'm not going to, I actually prepared to give the construction of non-separable extensions. I don't have time yet, so I will give an exercise. How to build a non-separable extension. You have k characteristic p. You have k of t. This is, the field of rational functions. K of t, and you take its extension. This is your base field. And then you take its extension by root of p power p of t. So in other words, you take this field, you consider the polynomials over that, and you take it by x power p minus t by this polynomial. This is an extension of k of the field of functions on rational functions over k. It's non-separable. Well, to see that, you just notice it's power p, so it's definitely non-zero on unity. I mean, it's definitely 0 on unity because it's p, its dimension is p, but then you have to do something for other. So it's an exercise. Okay. is now the theorem. So you have yeah. You have R over is the Artinian over K with trace form, non-degenerate. Then R is semi-simple. Semi-simple. In other words, R is direct sum of fields. Proof is one line. Yeah? Proof is one line. So you take you want to prove that it has non-importance, right? So we know that trace is non-degenerate. So trace to K of AB is equal to 0 for each A which is nilpotent. This is because nilpotent has a matrix. I mean, the product of nilpotent is nilpotent, and then nilpotent has a matrix which has 0 on diagonal, something upper diagonal, and this is clearly has 0 trace. So then, if trace is non-degenerate, then R has non-importance. Okay. Okay. Now I wanted to prove the last theorem for today, namely that the product of two finite extensions is direct sum of fields. So theorem, you have K1 over K, K2 over K is separable finite extension. Then K1 times K2 over K small is direct sum of fields. Well, this is the same as to prove that this is algebra which has no nilpotence because it's finite dimensional. And to prove that it is nilpotence, we check that the trace form is non-zero. But the trace form, it's not hard to see what happens with trace. So proof, if you have A is a matrix, so you have A inside K1, B inside K2, and then AB is so A is a certain is represented by multiplication by A is represented by a matrix, multiplication by B is represented by a matrix, and then the multiplication by AB is a tensor product of these matrices, for A and B. And this implies that, well, I'm not going to, I don't have time to explain what is tensor product of matrices, but it is something that you take a matrix for A, and instead of each entry, you put matrix of B multiplied by this entry. So you obtain a matrix which is, well, if you have two operators, you can have tensor product of these operators on the tensor product of these spaces, and this is precisely this matrix which we will obtain. And this implies that trace of A, B in that setup is trace of A times trace of B. So trace is non-zero. And moreover, it's non-degenerate. Because it's, if you think of this direct tensor product as a tensor product of vector spaces, then the trace form on this tensor product is just tensor product of trace form on these multipliers, on the tensor factors. And of course, tensor product of non-degenerate two forms is non-degenerate two form. This is part of the standard linear algebra. So this implies that if you have two fields with non-zero trace, then the tensor product with non-degenerate trace, then the tensor product is non-degenerate, has non-degenerate trace, because the trace form is a tensor product of trace forms on the sum of the components. Then this implies by this argument that this tensor product has no nilpotence, and then it implies that it is direct sum of fields. I'm done. So maybe you have questions? So I was proving the theorem that the tensor product of two fields is a direct sum of fields. As I told today already, I mean finite extension, so it should be finite dimensional. This would follow if you prove that there are no nilpotents. To prove there are no nilpotents, you compute the trace. And you check that the trace in the tensor product is a bilinear form, which is just a product of tensor product of two bilinear forms. If you have two vector spaces, V and W, you have bilinear symmetric forms GV and GW. You can define bilinear symmetric form on the tensor product of these two spaces by taking, you have an element V times W, V1 times W1, and G of this would be G of GV of V1 multiplied by GW of WW1. This is a bilinear, it's linear on each component, bilinear symmetric product, and its matrix is just a tensor product of matrices. So the determinant of this matrix of this bilinear symmetric form is just product of the determinants of these two matrices. And this implies that, in particular, if these two are non-degenerate, this is non-degenerate, and you apply this to the trace, you obtain that the trace of a tensor product of two fields is non-degenerate. If it was non-degenerate on these two fields. Okay, thank you very much. Muito obrigado. Eu termino.